Hi, good afternoon everyone. My name is GabrielFerreira Silva and this talk is about formalizing AC unification. I'm a PhD student under the supervision of Mauricio Ayala and my co-advisor is Maribel Fernandes from King's College in London. And the work I'm going to talk about is joint work done with my advisor Ayala, my co-advisor Maribel, but also with Daniele Nantes, which is a professor from mathematics, from the Department of Mathematics here in UNB. So here's an outline for the presentation. First I'll give a brief introduction, then I'll tell you about AC unification, pointing out what makes it tricky and the connection with linear Diophantine equations. After that I'll talk about a formalization of an algorithm that we have done, and then I'll conclude and tell you possible paths of future work. Okay, for the introduction. What is unification? Unification is about finding a way to make two terms equal by instantiating some variables. For instance, the variable x and the constant a can be made equal if we instantiate the variable x to a. Now, f of ax and f of yb can be made equal if we instantiate x to b and y to a, since both terms then become f of ab. And this, I want to point out that unification is a fundamental problem in theoretical computer science, which has practical applications in logic programming. So here you can think of the programming language Prolog, but also in theorem proving, type inference, and so on. Here's a diagram of the main related work. Stickel in 1975 gave a complete unification algorithm for associative-commutative functions, and he pointed out the connection between solving linear Diophantine equations and performing AC unification. There is also, however, Stickel's paper contained a flaw in the proof of termination. Fages discovered this mistake almost 10 years later in this paper here, Associative-Commutative Unification, and he gave a fix for that. Although there is no formalization yet of AC unification, our formalization was the first. Evelyn Contagian in 2004 formalized a certified AC matching algorithm, and she did it using the proof assistant Coq. As we will see, the problem of AC unification is connected with solving homogeneous linear Diophantine equations. So this paper here is also related work, a formally verified solver for homogeneous linear Diophantine equations. They used the proof assistant Isabel Hall, and these authors here are from the University of Innsbruck in Austria. Okay, the work I'm going to talk about here is in red. It's Formalizing AC Unification. We have submitted to the conference FSCD and it got accepted, and we give the first formalization of AC unification in this work. Previously, we had tried formalizing nominal AC unification, which is a work in the nominal setting, which means it's a bit harder than what we have in here, and we published our work in progress in a conference called UNIF in 2019. However, our algorithm was terminating and was correcting, but it was not complete. So this was actually a paper about a work in progress. This is a full paper, let's say like that. And this is what I'm going to talk about. Okay, AC unification. The problem of AC unification is unification in the presence of associative-commutative function symbols. For instance, if f is an AC function symbol, then these two terms, f of x, f of bc, and f of c, f of ay, these two terms can be made equal if we instantiate x to a and y to b. Since then, f of a, f of bc is, we say that it is equal modulo AC with f of c, f of ab. The order changes, but the the arguments of the function are the same, a, b, and c. Okay, what is tricky about AC unification? Here's an example. Let f be an AC function symbol, and let's think about the solutions that come to mind when we try to unify f of x, y with f of a, z. Well, you can instantiate x to the constant a, you can instantiate the variable y to the variable z, so you have the solution here. Or you can instantiate x to z and y to a. But are there other solutions? What do you think? And at first you think, oh no, there are not, but actually there are. For instance, you can instantiate x to f of a z1, so you introduce this new variable z1, and then you instantiate y to z2, so you introduce this new variable z2, but to compensate that, you instantiate z to f of z1, z2. And then both terms will be f of a, z1, and z2. Alternatively, you can instantiate x to z1, y to f of a, z2, and z to f of z1, z2. Now, I'll briefly explain the connection between AC unification and solving linear Diophantine equations via an example. So consider this AC unification problem here, where we have these two terms here, and we want to make them equal by instantiating some variables. Okay, according to the number of times each argument appears in the terms, we transform the unification problem into a linear equation on the natural numbers. So after this step, our equation becomes 2x1 plus x2 plus x3 equals 2y1 plus y2. Here, the variable x1 corresponds to argument x. The x here appears twice, so the coefficient is 2. Variable x2 corresponds to argument y. Y appears only once, so the coefficient is 1. The variable y1 here would correspond to b, and since b appears twice, it's 2y1. Now that we have this equation, what we can do is generate a basis of solutions to it. So in this table here, we see a basis of solutions to this equation here. For instance, the first row is one solution, where x1 is 0, x2 is 0, x3 is 1. Then the left-hand side is equal to 1. Now, y1 is 0 and y2 is 1, which means that the right-hand side is also equal to 1, and this is correct. Okay, by taking all the combinations of the solutions that compose the basis, so we take this basis and make all the combinations of these solutions, and we can obtain all the solutions to the original AC unification problem. And I know this is a bit vague, but due to time, that's the best I can do right now. There are more details in an appendix if you want to see. So in our example, the solutions will be, we have the solution sigma 1, which is equal to y goes to f of bb, and then z goes to f of a x x, and this is a solution. I'll leave for you to check, but there's also a solution like sigma 4, which instantiate x to f of z6b, so it introduces this new variable z6 and instantiate z to f of a y z6 z6, so it compensates that by also introducing z6 in the other side of the equation, let's say like that. Okay, now for the formalization, we have formalized that the algorithm given by Stickles. So in his paper, he gives an algorithm for AC unification, and what we have done is formalized that this algorithm is indeed terminating, correct, and complete. which prompts the question, why formalize an algorithm? Like, why not just prove the interesting properties of the algorithm using the traditional, what we call pen and paper approach? Well, when formalizing properties of an algorithm in a proof assistant, we almost certainly find interesting omissions, and sometimes we may even find errors in the traditional pen and paper proofs. Remember, for instance, that almost 10 years after Stickel published his paper, Fages corrected his proof of termination. So some errors may be discovered in this process of formalizing an algorithm. Here in the research group that I am part of, we use the proof assistant PVS, but some people like to use Coq or Isabel Hall or Lean. Those are just other proof assistants that you can use. And what we have proved is termination, correctness, and completeness. Yeah, I said that before. The original proof of termination was flawed, and only after almost a decade it was corrected by Fages. Correctness and termination, I think everyone knows what this means. It means that the algorithm does not loop forever. Correctness means that every solution in the output of the algorithm is indeed a correct solution. And completeness means that every correct solution, the algorithm can find it. So the algorithm outputs every solution to the AC unification problem. Here I have a diagram of the PVS files that I have used. I won't go into a lot of details, but I want to point out that this list here is actually more than one file, but it's not strictly connected to AC unification, so it can be used for other formalizations if people want. And we see here that it's not a very complicated architecture for our formalization. But what I want to say is that there are a lot of theorems that we needed to prove. A lot of them were easy, but the total number of theorems is over 1,000. It's 1,504. And this table here shows the number of theorems and TCCs in each file. TCCs means type checking conditions, which means that roughly that the types that you're passing as input really are the types that you should be passing as inputs. And these TCCs here, they were almost all of them were proved automatically by the system. So this part here was really easy. Maybe those here, those were a bit hard. So like 10 here were a bit hard, but most of them were really easy. And the theorems I had to prove, but a lot of them was manual work. Okay, for a conclusion and future work, in 2004, Evelyn Contagion formalized AC matching and left as future work for us to formalize AC unification. Matching is like an easier version of AC unification, so she left that as future work because it's a harder problem. It's now 2022, almost 20 years later, and now we have finished the first formalization of AC unification in the literature. As future work, I want to put our contributions in, we want to put this contribution in NASALib, which is the main library of PVS theorems and results. Then we can use our formalization as a basis to formalize more efficient algorithms, or we can extend the algorithm to the nominal setting, which let us treat free and bound variables in a natural manner. I'm currently doing this one here, and I want after that to extend the algorithm to the nominal. So this is it. Thank you. If you have any comments, suggestions, or doubts, I'm available. And I have here an appendix with the pseudocode of the algorithm, a more detailed example of AC unification, and one more statistics about the PVS formalization. But thank you very much.